Hello everyone, my name is Jonas El Gammal and today I'll be presenting you our new package GPry. GPry was developed together with my collaborators Jesus Torrado, Christian Fiedler and Nils Schöneberg as part of my master thesis. I will be explaining the idea behind the project, how it works and how it performs. Please consider downloading it on PyPy or just checking out the code on GitHub. Let me start by motivating the concept from a cosmologist's point of view. Typically, when we want to do parameter estimation with Bayesian inference, we have some physical parameters here, which then are fed into some theory code, which then computes some observables. And on the other hand, we have the data with possibly some usage parameters, which then together form the log likelihood or log posterior, which we then use a Monte Carlo sampler on to get marginalized quantities. Typically, what happens though is that as we get more data, our theory codes have to become increasingly complex, have to involve increasingly complex computations, so our likelihood gets increasingly slow. That is not a problem until a certain point when running this Monte Carlo sampler to get the marginalized quantities takes ages. That is partially due to an inherent weakness of Monte Carlo samplers. I will now explain the example of Markov chain Monte Carlo, but similar arguments can be applied to things like nested sampling. So while it is very easy to implement and quite versatile, the idea of MCMC is that there's a chain which runs in some random pattern, and that steps get accepted and rejected. The problem with that is that only a function of our likelihood evaluations are actually used as information to build our final marginalized quantities, because the rejected steps are then just discarded. And the other problem is that it essentially just generates a histogram of the points to get the marginalized quantities, which in higher dimensions, as we need more samples, becomes very expensive, as in we need a lot of posterior and likelihood evaluations to get those marginalized quantities accurately. So our idea was to develop an algorithm which uses a different approach, which I'm now going to explain. The idea here is to, instead of creating a sample of the distribution, interpolate the distribution. For that, we use a Gaussian process interpolator, a Gaussian process regressor, which essentially is a non-parametric way of interpolating a function using a kernel function, which then correlates the points. So you could probably, the easiest way to imagine this is that we assume that all points come from a joint multivariate correlated Gaussian, and the correlation between 2 points is determined by this function. So we get an estimate for a mean function, this, and an error on our estimate in a Bayesian way. Of course, it matters how we choose those hyperparameters. Not all kernels are created equally, and there's obviously a best way to interpolate. There's a way to derive a analytic log likelihood for this hyperparameter, which we could in theory sample. But the computationally cheap alternative is to just maximize this likelihood and then get maximum a posteriori to get the best estimate for this hyperparameter, which is what we're doing. The next concept I want to introduce is that of Bayesian quadrature. When we want to compute our marginalized quantities, we essentially need to calculate an integral of the posterior distribution, maybe not the full integral, which would be the evidence, but along some subdimensions. So since we have interpolated our function, with a GP, we can simply get a model for our posterior distribution, which we can then integrate by just doing the integral of the mean function. And also, now that we have this error bar on it, we can use this error bar to find the next most informative point where we could sample. This is called active sampling, and it's what we will be doing in our algorithm. Now we want to find this next most informative point to sample. For this, we take a so-called acquisition function, which we derive here, which essentially is just a function which we then maximize to get the next best point. For this, we can use two informations. A, we know that our posterior distribution is always positive, and B, we know that every little chunk, dx, contributes proportionally to its value to the integral. So if we take our posterior interpolation with our GP, we can see that a simple acquisition function would just be the mean, the dashed line, times the standard deviation, which is this width. Now, since our posterior distribution has a relatively high dynamic range, we transform it to log space because we can do that, it's always positive. And then we sample our log posterior, which then gives this function. If we transform it back to our original space with the added thing that we did a Taylor expansion here. So then there's two additional things. A, our points could have some noise, which could come from some numerics. So we want to account for that. And B, we know that our mean is not really correct at the beginning, at least. So we want to account for the fact that our mean could be off. And this is done using this correction factor zeta, which is set between 0 and 1. And I hope you can see this by subtracting this statistical noise from the sigma here. So essentially we suppress values which are very close to already sampled values. Here you can see this in action. On the top we have a function which is just a test function here, but could be a log posterior distribution. And on the bottom we have our acquisition function, which tells us where is a good idea to sample next. So if we maximize this acquisition function, then add this point, we get a new acquisition function and we can acquire a new point. So we can sequentially add more points to our GP till it eventually knows to interpolate our posterior distribution. The fact that we chose to sample our posterior distribution in log space, though, raises a different problem. In that, if our posterior distribution goes to 0, our log posterior diverges to minus infinity, and GPs can't deal very well with very large values, and especially not with minus infinity. So we have to find a solution to deal with that. Furthermore, a lot of theory codes will just return minus infinity for log posterior values far away from the fiducial value without even calculating things, because that speeds up. So our solution to this is an SVM classifier, so a support vector machine, which then divides the space into a finite region of interest and an infinite region where we're not interested in how the posterior distribution looks like, so we can just essentially discard it. So we put this SVM classifier in front of the GP, which then classifies this region. Here's an example of that. That's what it classifies as finite. This is what it classifies as infinite. And then we multiply our GP prediction with minus infinity everywhere where the SVM thinks it's infinite. So this is what this algorithm schematically looks like. So we have some initial point generator, which we then evaluate the log posterior of. And then we sequentially acquire points by taking the GP regressor and the SVM, which then tells us a mean and a sigma prediction, which is then fed into an optimizer, which optimizes the acquisition function for that, and that gives us a new location, and then we can go around. This part is our upper plot, essentially our interpolation. This is our acquisition function, and now we want to expand upon that algorithm. So the first thing you want to do is get several points at once from our acquisition function. This is handy because A, it allows us to parallelize our evaluation of the log posterior, and B, refitting this is very expensive. So it would be super nice if you could get several points at once, and there's a handy method to do that. It's called Kriging-Believer. And instead of evaluating our actual posterior distribution, we just assume that our posterior distribution is roughly the mean of the GP. And then you can show that this mean function doesn't change, only the sigma changes, but with that you can already calculate a new acquisition function. Obviously this is just a lie, you're just essentially lying to the model. But with this method we can acquire several points at once, then interrogate the true log posterior, refit it, and then we can get another batch of points. This is an example of that. So here we have our true function, which is just a parabola, so the log posterior of a Gaussian in this case. And this is our mean that we have generated from just 3 points. And there we do 3 steps of this Craigen-Believer. So you can see that the acquisition function changes, the mean prediction doesn't. And then we can interrogate our true function, which then gives us this. Okay, this sort of overfits, but you get the idea. Next, we want to find a stopping condition for when to stop the algorithm, because we don't want to do this forever. We just want to do it until it's converged. So for that, we just use a very machine learning way, which is that we take the difference between our evaluation and the prediction that the GP gave us before we evaluated, and see if that is within a certain small range, so a small parameter alpha, times a relative parameter, which is the difference between our the maximum evaluation of a log posterior and the one that we got. So essentially we penalize being very close to the maximum, because there we want to be especially accurate. And far away from it, we allow it to be a bit less accurate. And then we just essentially have a value at which it stops. Lastly, we of course want to extract our marginalized quantities. So right now we only have our GP interpolator, which is a function we can call, but we don't have our marginalized quantities, we don't have our nice corner plot. So the way we do that is that we run then an MC sampler on the GP. So that sounds a bit stupid at first, because we avoided having to use MC samplers. But the idea of that is that if our interpolator is much faster than our actual log posterior, this MC sampling is going to be super fast, and we can conveniently get our marginalized quantities from it. And then we can do our nice corner plots with that simply. So now for the fun part, the actual experiments and how it performs. So I chose these 2 examples first to stress that a lot of people ask whether this is just putting a very strong constraint on the posterior distribution to be a Gaussian. This is not the case, as you can clearly see here. It can also model very non-Gaussian cases. We are only putting a constraint on the differentiability and assume that the posterior distribution has a single length scale along each dimension, which is also a relatively weak constraint. So we can model things which are highly non-Gaussian. There are limitations, which I will come to later though. And since we are at a cosmology conference, let's look at some Planck pictures. So this is a Planck light run with the 6 physical parameters. And as you can see, within 250-ish samples, this converged very well and reproduces the right contours. And this is a Planck full run with the first 20 parameters plotted. It's actually 27. This is supposed to show sort of the limitations of what it can do. So as you can see, it recovers the contours very well. I mean, there's some covered by my face, but you just have to believe me that they're good. But this, I wouldn't call this very stable. I wouldn't confidently say that you should do that, but it can do it. Now for the elephant in the room, the computational overhead. Because anyone who's ever worked with GPs will know that they unfortunately scale very badly with the number of samples that you add. This is due to the fact that refitting the GP hyperparameters requires many inversions of the kernel matrix, which scales with the number of samples cubed. and predicting a single point scales with the number of samples squared. This means that we are essentially limited to, let's say, 1,000-ish points, which imposes some limitations, which I will go on to in a bit. So here you can see the time it takes for a single iteration, which is 2 Craigen-Believe steps. This is a 8-dimensional Gaussian example, so this in total is 300 accepted samples in the GP. And here you can see the number of evaluations of the GP. So this blue one is prediction, and this orange one is this matrix inversion, which is also why it scales so badly here. This neatly brings me to the limitations of this algorithm. So first, there's the problem of multimodality. As you can see, this is the Himmelblau test function, and there one mode is completely missed. This doesn't always happen, but it can happen, so multimodality is not officially supported right now. The second problem is that of overhead. As you have already seen, the overhead grows considerably with the number of samples, so we are essentially limited to at most a few thousand samples. Then the third problem, as you've also already seen, is that limiting the correlation length in the kernel, i.e. preventing overfitting, is sometimes a problem. This very rarely happens, and only if the mode is already characterized very well, but as you can see in this case, then the acquisition function essentially just returns nonsense. Then another problem is the dimensionality. This is connected to the overhead problem, in that in higher dimensions we need vastly more samples, and then it easily becomes computationally prohibitive to do it. So about 15 dimensions is the realistic maximum for most cases. And then there's the problem if there's vastly different correlation lengths in the posterior, like a very wide mode with a tiny spike or something, then it can also run into problems. Now you have made it to the end of the talk. Here's some practical info, most importantly the links where you can find the project, where you can download it. Dependencies are the Cobaya package, sklearn and MPI4Py, and most importantly, it works with Cobaya models. So if you have a code that already is running in Cobaya, it will work in GPry. And that is the end of my talk. Thank you very much for listening, and hopefully see you in the discussion session.